Awesome. Okay, we're going to get started. We're going to talk about Caliptra's unified testing methodology. So it's like core is like he's an engineer from Google who works. He's a big like contributor to Caliptra, as well as myself from Microsoft. So we're going to talk through. So while we were developing Caliptra, we thought through like different methodologies on how we want to go about developing the test cases. And we experimented a bunch of stuff, and I think we have landed up at a good spot, and that's what we're going to talk through. So unit tests is like normally where people start testing. They're great, fast to write, easy to execute, and easy to perform code coverage as well as fuzzing, right? So they're great. But they do come with like some sorts of cons, and specifically the cons are around. They are not normally compiled for the target machine. They're compiled for the host that you're running your development environment in. There are a set of defects like stack overflows, watchdogs that are difficult to catch in in unit testing environment. There are also areas where it's difficult to write unit tests for things like depend on interrupts, DMAs. So it kind of becomes complicated to simulate such situations. So if we are simulating at the best. Also, many times we have seen that unit tests do make bad assumptions about the hardware, how the hardware behaves. We had run into similar problems ourselves, so it kind of becomes challenging. It also 100% code coverage isn't really realistic, and they can be brittle, right? Because they're written against the APIs. As soon as you change the APIs, they break. So unit testing has challenges too. Integration tests, normally they're written for end-to-end scenarios in perspective, so they can really be run on real machines, right? As well as RTLs, pre-silicon environments. And 100% code coverage of real scenarios is possible. And the assertions, they don't have to be done within the test. You can observe the the outside, to see you give a stimulus what the output is. So there are so they're pretty good that way. Problem is they're difficult to write, right? And they depending upon what your integration environment is, you can't always write exhaustive tests. And also right, there might be redundant tests that run in RTL environments, full system emulators, FPGAs. You have to customize the test cases to run in different places. And again, right, coverage guided fuzzing is complicated. However, at least we figured it out that we can fix these things by taking looking at the deeper at the RTL models we have. Next slide, please. So this is kind of the high level top level SoC diagram of our verilator environment, and you can see there's a CPU, the CPU, SRAMs, mailboxes, and the crypto peripherals, and there's an external APB slave. So what we really want, if you want to write good integration tests, we want to be controlling some of the registers as well as the integration stuff coming from outside. For example, the signals that are coming into Caliptra as somebody would integrate the IP, as well as the registers that control that are controlled by the SoC side. So hence we land up at a model that Core is going to talk about next.
Okay, so basically we want to write the same test case once and then have the test case run in a bunch of different modes. Cases, and I'll go into detail what the different environments they are, but before we get to that, I'll just kind of describe the high-level API that we want to use to talk to a hardware model. And so the hardware model API is used directly by the integration tests, and it provides an abstraction to configure all of those various signals. So we want to control what boot ROM the device has. We want to manipulate reset signals, any other signals that come in, like the TRNG signals. We want to manipulate the passage of time. Sometimes you want to test very specific timing conditions, like what happens if the SoC does this weird thing at exactly this right time, and so we want to control time execution or control time. And for stuff like verilator model, that means toggling the clock signal as needed. And then with the other models, there's other ways to do it. And we manipulate, of course, the APB bus signals itself. And then we also want higher level things we want to do as well, and we'll just kind of bundle these into the same API. Like a lot of tests, they're just playing with the mailbox interface. So let's provide high level functions that can do stuff like uploading firmware or sending mailbox commands, that sort of thing. So here's some example code that I just copied from a test. So you can see here we're just constructing the model. I'm giving it the contents of the ROM I want to use and setting up everything, all my other initialization parameters to the defaults. And then I'm asking it, OK, this ROM is going to print out hello world. And so I'm just asking the model, hey, step until you see the output hello world. And then that's going to stop execution at that point. And then I can write something to the APB bus. I'll say, OK, let's write to the mailbox address command the word 4242. Now we have a little bit, we have this whole register abstraction interface that we use in Caliptra, and I've actually enabled it to work in the test cases as well. So rather than having to, write to use this, address value type API, you can also just use the typed values, which if you've used any of the Rust libraries like SVD to Rust, the API is very similar to that, where it gives really nice ways to set all the different fields in a register. And so this here I can translate or write the same way, just saying, use the command register in the mailbox peripheral and write the value of 4242 to that. And then similarly here is an example of a test case. Let's just move time forward until we see something written to the error info register, right? So just kind of a rough idea of what our test cases can look like. And now I'll talk a bit about the different models that we provide. And the first one is the full system simulator. So if you've used QEMU before, this is kind of the same idea. It just is you're emulating not emulating, there's a CPU interpreter running the code, and then you've made software implementations of all the peripherals. And so this was made really early in Caliptra's timeline by Vishal. He set up an emulator or a full system simulator that worked and we could write code for before we even had really working RTL. And so we could start work on the ROM and other device drivers and stuff before we had RTL to talk to. So it consists of a RISC-V interpreter and then a bunch of peripherals. The tests themselves just embed the interpreter and all that logic in the actual test binary itself. So you just use it as a library, and these tests run really fast. Most tests run less than a second, but they're low fidelity. We didn't simulate all the exact timing of everything. So they're good for high-level checks and really fast validation of your code and tracing through what's going on and for rapid iteration. But they're not really going to give you the confidence that everything's fine. And this simulator can run the exact same binaries that we would ship to the world. So we use these. We run basically all our tests in this environment as part of the pre-submit. So it only takes a few minutes to run. And we can get instruction level coverage data out of it, and we can log. If you want to debug things, you can get a log of all the CPU bus activity. And we have because everything is just software, we want to tweak the hardware to the implementation to fake out weird hardware or misbehaving stuff to test some edge cases in the code. We can do that, which might be harder to do with the real RTL. And then there's the second hardware model, which is basically using verilator. So we take Calipra's RTL, and we compile it with verilator, and then the test cases, or the hardware model implementation, will basically just feed the signals into the verilator model from the test case. And so this is very high fidelity, cycle accurate, but it takes a while to run. So for example, to run all of our tests takes over 36 hours on a huge cloud server. Execution is really slow. It's terrible. But it's great for debugging hardware issues. And when you can take any of our tests and you can say, have it generate VCD or waveforms, so you can dig into why something's failing. And early on, when we were first integrating with the RTL, there was hardware bugs that we found on the software side. And so having this ability to point the engineers at, hey, what's going on here? This signal doesn't look right, is really useful. And again, we can parse those waveforms and get nice trace logs of the bus activity, which is a little more user-friendly. yeah, we run a few important tests every night. That's actually not true anymore. We now run all the tests every night. We're just spending a lot of money on cloud resources. But verilator's not perfect. It doesn't really do clock gating very well, and so some of the situations we can't test under verilator. And then there's hardware number 3, which is well, there's actually I guess 4 now, but we'll say 3 is the real-time FPGA. So this is just the FPGA running real-time. It's very fast. We can run tests in seconds. And in our case, we're using a Zinc FPGA. It works well. So this particular model, the real-time model, is using the clock on the FPGA dev board as the input to Caliptra. So the test case doesn't have the cycle-accurate control, but I actually am working on a version of this that gives us cycle-accurate control again and lets us basically have all the flexibility of all the models. So the 4th model, which is the synchronous FPGA model, will be even better. But this presentation was made before that worked. That was a thing. The main downside is that you can't really iterate very fast on the RTL. It takes hours to get a new bit stream. So now I can do a quick demo. So here, for example, is our smoke test. And I'm sorry, let me just. What the heck? So this is kind of our main test, the happy path test that just tests the Caliptra boot and makes sure that all the certificates generated are correct. And so I can just run this here, and by default, our tests just run under the full system simulator model. So you can see compiling the firmware, and then it runs, and oh, there's it passed. Yay, 2.5 seconds. That's just running on my laptop, and the environment with this testing is really nice. You can edit the firmware, hit the button to rerun the test, and seconds later you can find out whether your test passed. Like it's, the ultimate firmware development environment. And similarly, we have actually we can do the same thing for the FPGA. So here is, hopefully this SSH connection is still open. Yes, it is. So here I am running the same test on the FPGA farm. And so it's compiling a test to run on the ARM on the application CPU and the FPGA, and then it runs it, and 1.8 seconds later we ran the whole thing. This is running with the real Caliptra RTL, and we can run all of our test cases in this environment, which is fantastic. And then similarly we have the verilator model, and if I was to run that same test, it would take, I think, 6 hours to run, so I won't do that. But there's some other tests that I can run that go faster. So then here's a different test that's just testing out basic mailbox communication that runs in a few seconds. But that's like, I think, on the order of 10,000 clock cycles. And I think that's pretty much it. Again, and the same slide that everybody else has been showing off, but yeah, come help us out in Caliptra. Take a look at what we're doing. Maybe we can take some of the stuff that we're doing is useful maybe in other projects, and maybe we'd accept contributions to kind of extract some of this stuff into general purpose libraries and frameworks. I'd definitely be interested in that. Thanks. Any questions? All right.
Thank you.
Yeah. Oh, sorry.
Yeah, I'm just curious. This is really fascinating, actually. Thank you for sharing it. Do you have anywhere that's a good place to take a look at the design decisions that you are making?
Ooh.
So it's a great overview. You probably have a lot. Have you written any of that down?
I have not written down design decisions, but I have written down the implementation in terms of source code and and GitHub Actions workflows. But I'm happy to talk about it if you're interested, and maybe we can write some docs. I don't know.
It's been fairly organic development.
Yeah, this is very much organic. Like, oh, we need something that does this. Well, let's just build that. And, like I've just finally kind of got the impetus to do this synchronous FPGA model, and that wasn't on the roadmap originally.
I guess this is a design decision question. Why did you choose Rust?
Okay, this is a great question. And actually, I'm surprised you didn't really bring up Rust at all with Caliptra. I've been a Rust proponent for way too long, and I'm too biased. But basically, 2023 seems to be the year that the powers that be are like, yeah, go ahead and use Rust. We think it'll work. And our experience has been very positive. I'm sure Vishal can talk a lot about that. Actually, maybe I'll let you.
Yep. So I think a few things, right? Like, memory safety is the primary one, right? Like, it has historically been, C has been challenging, like in terms of nasty bugs, in terms of like, pointer, dereferencing bad addresses, like stack overflows. Rust kind of gives us guarantees, provided you're writing safe code. Unsafe code can be challenging, and you have to be careful. But overall, it's been like a fairly pleasant experience. The tool chains are really good, right? Like integration into editors and stuff like VS Code, like like how it just like improves the programming experience. So, and it's a security processor, so Rust did make sense when we're looking at what are the options.
So just as an anecdote, in the entire Caliptra project, I have not debugged a single runtime, an undefined behavior type issue at all. Basically, if it compiles, it's pretty damn close to doing something which is sane. And the only real issues is the function, is what it's doing, what you actually want. But it's trying to debug a lot of like the machine going off into the weeds. Like we have these trap handlers that I've never actually seen fire because we never had any kind of bus error. Oh yeah, and also one of the things that we do with our firmware is we disallow all panics. So the continuous integration checks to make sure that there is no panic calls in the entire firmware. If you try to submit a PR that introduces a panic call, it will fail on you. So this basically means that typical stuff that would cause Rust panics, like probably the simplest one would be a bounds check where you're going past the end of an array or something like that. You can compile the code and you can play with it, which is great when you're just playing around. But if you try to submit code, we'll reject it. And so yeah, there's basically no runtime abort type calls in our firmware at all. Right.